All right. Hello, everyone. Welcome, welcome. I hope everyone's having a lovely afternoon, or whatever time zone it may be where you are. I am back. I'm back to my normal stream setup. I finally got a sound font other than that horrible sound font we've been using over the break. Yeah, I'm in high spirits. I did forget to place the order for the button boards, but I'll do that after stream this time, I promise. But yeah, that's certainly not going to stop us now. This stream, we're going to be doing more soundboard work. Just to be clear, the syrup project is what I'm calling this soundboard, because when it's done, I'm going to be putting it on Pancake. Pancake, of course, being my girlfriend, who I am making this as a gift for. So yeah, might as well jump right into it. Let me go ahead and put on our background music. Oh no, where have I gone? It's okay, I'm back. Press this button. I remember my key commands. I remember all my keybinds. Don't worry about it, chat. Alright, so when last we left off, we were mostly working on the button board, which was... Let me open that real quick. Project right here. I made a few slight changes. If you follow me on Mastodon, you might have seen this. It's like the color scheme is different in this install for whatever reason. I'm not sure why that's green. Oh well. All the same. I added a little bit of extra silk screen text. Including a link to the repository and a description of what it is. Those of you who weren't here last time, this board is meant to hold a ring of WS2812B programmable RGB LEDs. Those LEDs are D1 through D7. D1 through D8. On the board here. They'll rest on these pads. You'll notice they are very small LEDs. They've gotten those WS2812s down to a real tiny size. And we're not using too many of them. Mostly because we're going to be having 25 of these boards, and I want to make sure that we're not going to exceed our power requirements. Now this, incidentally, is a nice way that we can sort of gracefully degrade our performance as the power available decreases. As I mentioned last time, these things would only draw full current if we're using all of them. So if we only have, say, 500 milliamps available, what we can do is we can program it so that only two LEDs on each board are active at once. That'll still provide some nice colors without needing to use the full 8 LEDs per board, 8 times 25, 200 LEDs times whatever their power consumption is. So yeah, that'll be a nice way for us to sort of decrease our power consumption when we need to. That will be controlled by the microcontroller, of course. We'll need to remember to implement that in our firmware as we program it. Let's see. So yeah, as we've been over previously, these two resistors right here are what let us determine A, what the orientation of the USB port is, because it can be plugged in two ways. B, whether it's plugged in at all. And C, how much current we can get from it. Excuse me, chat. The amount of current is determined by the voltage level on these pins, which we can read because we have them connected into analog to digital converters on our microcontroller. So CC1 is connected to PA6. CC0 is CC2 is connected to PC4. Both of those are ADC inputs of some variety. I don't remember exactly which ones, but we can pull up that document again if we need to. So yeah, just in review, the USB-C spec specifies that essentially we can only draw 100 milliamps when our device powers on. However, with most USB ports, we can draw up to 500 milliamps. We have to negotiate that during power up. I believe the firmware on our microcontroller, the hardware on our microcontroller will take care of the hard bits of that. I suppose it might be a firmware library. I'd have to check in with that once we get to the programming stage, but we shouldn't have to program all the handshake negotiation stuff ourselves. Long story short, the microcontroller will do that for us, hopefully. And so we can negotiate, usually on a USB-A connection, up to 500 milliamps. We're using a USB-C connector. That means that we can do the USB-A. That's like our sort of minimum, because you've probably seen a USB-A to C connector there, right? Somewhere out in the wild. So we do need to be prepared for the possibility that we'll be connected to a USB-A port. That being said, most direct USB-C connections will give us at least, I believe, 1.5 amps and possibly 3 amps. So we can definitely make use of that if we have that power, but we have to make sure that we check whether we have access to that power. Because A, we want to be in spec. B, we don't want to end up frying anyone's USB ports. A well-designed USB port will be able to shut our device down automatically if we draw more current than it can handle. However, have you seen humans designing things? Like, listen. You know, this is a human positive stream. We love humans on the stream. But humans sometimes make poor design choices and sell them. So we can't rely on a well-designed USB port, and we have to make sure that our device is within spec. So yeah, this stream, I think the big things we're going to be doing, we're going to add the parts on our schematic for the connectors. So the wires that will connect to the LED boards. We're going to add the button hardware to our schematic. We're going to add the debug headers. We need to add those. And then once we have that, we can probably start PCB layout, which will be exciting, but also will require us to think about a new aspect of enclosure design. Because, of course, the shape of enclosure we go with will determine what shape we have available for the PCB. Now, I am planning, by the way, once we get to that stage, try and use FreeCAD for the enclosure design. FreeCAD being it's a CAD software sort of in line with something like SolidWorks that lets you design three-dimensional objects and define them in a very precise way. So you can do something like, basically it uses this concept of sketches. Yeah, this is my first time using FreeCAD for any projects. I have experience with SolidWorks and Autodesk Inventor, but none with FreeCAD specifically. So the general flow is you make a sketch, and that sketch will be something like, I want a circle with radius 50 millimeters. Oh, no. Okay, that shortcut doesn't work here. And you want a circle, and I want that circle to have... Look, very nice. I want that circle to have a diameter of 50 millimeters. I want you to open that sketch. We need to edit it. Hey, edit sketch. There we go. So you can see on that text on the left, fully constrained. That means that this model or this particular sketch is precisely defined in all dimensions. If we wanted to do something more complicated, let's say we wanted, let's see, we wanted like a diamond of some sort. Now you'll notice that we are under constrained with 6 DOFs, that's 6 degrees of freedom. That basically means that we can like move around parts of this because they aren't exactly defined where everything is. Now you'll note that some of these are constrained to specific axes. And that is because the program will automatically place some constraints as we it'll automatically place some constraints as we go if it thinks that we're likely to need them. But some constraints we have to place manually. So if we want to say, make sure that these two lines, make sure that all these lines are equal length. So that 4 degrees of freedom we now have because we, by setting a coincident constraint, I'm sorry I didn't explain this, by setting a coincident constraint on these two points, it says basically make these in the same place always. That essentially connected this shape up. If we wanted to have all of these lines be the same length, we select them all and we hit the equal constraints. Let's see. I think that didn't quite work as it should have. So now these are equal in parallel, but they can vary independently. We add one more equal constraint here. That should. I wonder why that says redundant. Is strange. Well, if we constrain those to be perpendicular. Again, you'll have to forgive me. I am learning as we go here. This is, I'm familiar with programs of this type. I'm not familiar with this specific program. If these two are constrained to be perpendicular, it has essentially the same effect. I'm not sure why that equal constraint didn't work, though. But yes, now there's only 1 degree of freedom, and it is the radius of this interior diamond, which we can constrain by adding a dimension to that distance. If we want this to be 8 millimeters, like. Okay. Now this is fully constrained. We know exactly what this is, exactly what shape this is. Numerically speaking, we can take this sketch and so it's called padding in this program. We want to extrude it maybe 20 millimeters. Why not? So you can see now we have a three-dimensional shape that is very exactly defined by the combination of the dimensions on this sketch and the length dimension on this pad operation. And we can also do things like add a fillet to this edge. Let's see where that is. There it is. A fillet is just this curved surface. It's basically just saying round the edge. The sort of sister operation to the fillet is called chamfer. That's the same thing, except instead of being a smooth curve, it's a straight up diagonal line. So we can have a fillet on the outside, a chamfer on the inside. And let's say we want a hole going through the middle of this thing. Make that on the XZ plane. Oh, to be a hexagon, why not? Okay, now this right here, this is not helpful. I have to admit, this is not helpful. I want a... have away view. Ah, they do. Yeah, there we go. So if we're using a front view here, want to edit this sketch. Size this down. We want this line to lie parallel with the x-axis. Specify that. We want these to be parallel. There we go. Can I project geometry in this? Like I said, this is a first time using this program for me as well, doing this little demo. I'm seeing what exactly we have here and what we don't. In AutoCAD or in Autodesk Inventor, you can take a geometry like, say, this top sort of surface up here, and you can project that as a line into the sketch, which is useful for creating like midpoints and things like that. I don't know if we can project geometry here. I'm very happy that there's open source software to do this now. Because let me tell you, getting actual, like, Autodesk Inventor is a pain. It is not cheap at all. You see, there is, yeah. Yes, getting a copy of the, like, sort of original closed source 3D CAD programs costs quite a lot of money. Open source software provides a very nice alternative. So it may be missing some UI polish and things like that. External geometry. Oh, there we go. It does have this feature. That is excellent. So then we want to create a construction line between these points. Construction geometry is just geometry that isn't... It's not actually, like, physically there. It exists as a convenience for it exists as a as an aid for constraining things, basically. So you can think of it like when you're, you know, if you've ever constructed something with a compass and a straight edge, all the lines that aren't part of the final shape, right? They're just construction geometry. The same principle applies here. I can find the button for it. I'm pretty sure this program has construction. Yeah, there we go. Oh no, this is boring. It considers this to be over-constrained. If something is over-constrained, then that means that there are too many constraints. Like, it is not just constrained enough. Like, there's a level of something being constrained enough so that we know exactly what it is, and then there's the level of it is so constrained that there's redundant information, and you don't want to have that. Usually you want to have just exactly the amount of information you need to properly define your model. I'm thinking better not to include this line. Why is it not over-constrained now? What? Oh. That considered over-constrained. Oh. Strange. Oh, this millimeters up. For constrained. We have not constrained the size of the hexagon. Vertical dimension. Was I the dimension? Unfortunately, this can sometimes be a flaw with open source software. It can be a flaw with any software, I suppose. There's unfortunately a lot of polish that gets left by the wayside in open source software sometimes. There are some projects that are very, very well put together, but they tend to be the exception rather than the rule. Now we can make a hole of this. Let's make a hole of this. Let me turn the clipping plane off. That's one way. Let's see if we can convince it to cut through both ways. This is really weird. So when the keyboard command to do this is shift right click. And once you've pressed down right click, it'll keep doing this until you let go of shift. So if I've let go of right click now, and it's still dragging until I let go of shift. Very strange design decision. Let me actually set a clipping plane here. That. Now we can more easily see what's going on here. Symmetric? Oh, hey, there we go. Hey, looks lovely. So now our funny little gadget is made, and all of this is extremely well defined enough that you can create the exact same thing a million times. We wanted to let this just a tad, a teeny bit. I'm not sure what... It seems like the fillet is strangely not quite symmetrical. What edges we want to fillet. I wish if that was done differently, because having an asymmetric situation like this is not... Like I said, the goal of CAD programs like this is to have something that will be like the exact same. And having these, you need to be able to control every last detail of a part, you know? And having this weird fillet system where sometimes it's filleting edges differently. Why is it happening there? I would have liked to see that implemented differently, but perhaps that'll change in the future. In any case, for our purposes, that's not very significant. Sort of an acceptable issue to have. Do the same thing on the other side. Yeah, and then we can presumably export this as, like to export this object. Export this as an STL. Yep, so this is a file that can be 3D printed. Just stick this like and then so if you follow me on Mastodon, that is digiment@mastodon.social, although soon I think I will be moving that to a new instance. If you follow me on Mastodon, you will know that I've recently placed an order for a new 3D printer, which is really exciting to me. It's been a few years since I've had one of those to play around with. We're going to be using that to make the enclosure for this device. And I know I'm certainly going to be using it for a bunch of other stuff. But yeah, as soon as I get that, I guess this will be a test print for it. Okay, so that was just a little sneak preview. Wanted to play around with that software a little bit. That being said, that's not our goal for today. Today, what we want to do is create the LED board connectors. Those are just going to be the connecting headers to the LED boards, as the name would imply. Down below here, we're going to have our buttons, the buttons themselves. Start out with these LED board connectors. We'll be using the same part that we used here, as it will be the same connector. Just copy over the information here. Oh yeah, I should fix this. We can export all of that to other sheets, and that'll show up here as well. There we go. And place the connectors themselves from the component library. Give KiCad a moment to load everything. Turn this up a little. I think that should be fine. My mic levels seem to be high enough. As always, if you notice any issues with the sound, if the music's too loud or too quiet, if my voice is too loud or too quiet, or anything's cutting in or out at all, just let me know. I would be happy to fix it. Be from the same library, right? Yeah, let me take a look at that then. Possible something just needs to be refreshed on this end. I wonder if it didn't survive the trip over. Let me real quick check on my other system. I have my laptop right here next to me. I can open it up and take a look. Apologies for the delay. Look, we're opening syrup.kicad project. Opening that symbol library. On the full syrup project, that's not there. On the button board project, however, take a look. It's also not there. What's on there? Well, you know what? Maybe we only have a footprint for this. Oh, yep, that is true. So it looks like we don't have a schematic symbol for that, although I should fix that. Sorry, this gave an error last time that it couldn't load the syrup library. What is going on there? They, looks like KiCad's using absolute paths for this, which is not good to do. We will have to, take a look at that later, but the button board isn't what we're focusing on right now. I should make a symbol for this. I should make a dedicated symbol for this. In general, it's best practice to have properly labeled symbols for all of your components. Instead of just generic, like pin 1. Oh, most nights I'm just wearing my pajamas. We're wearing our pajamas again, chat. But yeah, we shouldn't just have unlabeled like pin 1, 2, 3, 4. Because then it's hard for someone looking at this to know what those pins are. And what they mean on any given end of the connector. So the best thing to do is to implement our own symbol using that footprint. And we can do that real quick. Symbol name. J is usually the symbol used for connectors. see. That is pretty good. Really pull open the schematic so I can see which pin is connected to what. VCC is connected to 4.
I want to fly away, far from my mistakes.
Showing
Just too much weight, so my bed is where I stay. I want to fly away.
why is this showing below this? Can I change that?
My baggage has too much weight.
The Z order.
So my bed is where I stay. Tell the clouds that I say.
I'm assuming that's what that is. Yeah. I guess we don't need it to be filled. Oh well. That's supply, ground, CITO. These would be power inputs. I guess we should have a specific symbol for this into the connector, because this would be a power output from the perspective of the main board. VI. O. Gotcha. So that should be the O like that. Pin number 1. That is an input because remember that we send data to data in because that's data in of the LEDs, and we get data back from data out. Make this thing a bit smaller. Well, you know what? Give me just one moment. I will be right back. Just a second. I'm back. So turn off some lights to hopefully make my model do less weird blinking. Let's... Okay, so I guess there's no way to, like, modify it if it's... Okay, so we have to change this. Wait, what happens? What? Wait, did it delete? What? Did it delete all of them? What are you doing? Oh, okay. What is happening with this library? It's this card changes and reopening it. Again, open source software sometimes has these issues. And closed source software also sometimes has these issues, but they tend to be more pronounced often. In open source software, at least. KiCad, thankfully, is a relatively stable piece of software. You usually don't see a lot of issues like that. So we're not going to derive this from existing symbol. Yeah, I'm going to do that. What we are going to do, though, is copy over this, change the types around. BCC is a power input. Ground is a power input. Or no, wait. Output is output to the rest of the circuit. That's right. You'll have to forgive me. Editing symbol libraries, I can sometimes get a bit confused with the directions. The I is an input to the rest of the circuit. The O is an output from the rest of the circuits. So the way these RGB LEDs work, I believe this was explained last time, but I might also have forgotten to. Let's see, power input from the rest of the circuit. Okay, yes. So they only have a single data line. Data is pushed in serially. And basically it just goes in this large daisy chain to all of the LEDs. So when we have this system fully set up, again, there will be 8 times 25 equals 800 divided by 4 equals 200. There will be 200 LEDs. They will all just be daisy chained with the outputs, with one's like data outputs, the O, connected to the other one's data input, the I. And one long chain, and you saw me doing that on the button board, but the same thing will happen between the button boards. So that at the end of the day, every one of them is connected in one long line, and we send out a stream of data one at a time that gets sent between the LEDs until eventually all of them have their data for a single frame, and then we start sending the next frame's data. That makes sense. So we send it all out in series. And it travels all the way down the line until it reaches its target LED, essentially. Okay, there we go. So we're going to want to update the button board at some point, but we don't have to do that right now. So we want 25 buttons. Which means we're going to need to place 25 of these. I believe we can set the default, somewhere around here, I believe we can set the default footprints. So we want to use our, disconnector. We do the same thing on the main board connector. Define that footprint as the same thing from before. Oh, you know what that all units are interchangeable thing is for? It's for things like if you have a package that has like 7 different resistors, or that has like, 8 different resistors, but they're all on like one chip, so like you have pins 1 and 2 are one resistor, etc., etc. I don't think that's actually a chip, but it's, something like that. Actually, I think there are like surface mount chips that are like that. Anyway, if you have something like that, so that like, the resistors are all the same value, so there's really no difference between using pins 1 and 2 or pins 3 and 4, because they're both resistors of the same value. Then you say all of the like subcomponents on this chip are interchangeable. If that makes sense. We scroll down and place all of our connectors. Why those are there? That's not where I placed it. Oh, well. These like here, so we have room for stuff up above. We want to copy paste one there. So we want to try and find copy paste. There we go. That is 25 button board connectors. Like I said, just want to chain the output of one, the input of the other. Of one to the input of the other, output of one to the input of the other, etc. That's not correct. There are those. There we go. Just going to be chilling and placing down connectors for a little while. Hope whatever y'all are doing out there in chat, you're having a good time. Are staying warm. Or depending on where you live on Earth, staying cool. I know here in Chicago, I suppose I wasn't here for the end of December, so it could have snowed there and I just wasn't seeing it. But I know that we're having the first bit of snow that I've seen this year. Well, we had like a freak snowstorm on Halloween. Other than that, this is the first snow I've seen all year that actually stays on the ground in Chicago. Just joined a moment ago. Why are we changing the outputs to the inputs? Okay, so these are the connectors for the button boards. Let me see. Let me pull up the PCB real quick. I think that'll make it a little bit clearer. So each of these diodes, D1 through D8, they're not populated right now on the diagram, but those are WS2812B LEDs. They are programmable RGB LEDs, and they are programmed in a chain, basically. You have a line of serial data that has the red, green, and blue value for LED 1, and then the red, green, and blue value for LED 2, etc., etc., etc. All in one single stream of data that goes in and out through every LED in the chain. And basically, you can see on the button board itself in the schematic that the data out of one goes to the data I of the next. And that is done that's done so that basically you only have to send in one stream of data through this DI inputs, right? That just goes through every one of these LEDs in a sequence until it's daisy chains basically through the whole line. Thought the components I was daisy chaining were buttons and not LEDs. Nope, these are actually just connectors. So these are the board connectors that would basically each one of these connects to this connector on one of the button boards, and there's going to be 25 of those total. So they have them all daisy chained up in sequence. Welcome in, Wimby. Hope you're having a nice afternoon. This to be the same length, so I'm just going to copy paste these over. So we can know where to put the lines going down. That is all 25 connectors daisy trained together. Make more sense to have the power input on top, wouldn't it? Standard board power connection. Put this around. There we go. Hear this a bit better? Go ahead and break this out. Be an input. That bold, but this isn't bold. Set it to bold. There we go. All right. That needs to be a bus connection, doesn't it? But it even keeps the color. Except for the joint. And then we want to add that here as well. Now, I don't think... Let me think about it. So, the WS2812B protocol is a bit strange. I would rather see it in a data sheet. Yeah, there are very specific timing requirements for the pulse length. Let me see. So, if I remember correctly, I know that the ESP32 has a infrared remote protocol, or an infrared remote peripheral that automatically generates like codes for generating remote signals that you use for like a TV remote or something along those lines. And that can be used to make this protocol happen. But we could also just bit bang it. I'm going to do a quick look and see if we have anything in here that could theoretically help us. I mean, the nice thing about this is, remember, I'm coming from like 8-bit ESP32 worlds. The 8-bit ESP32, that's not a thing. 8-bit, like 18 mega worlds, where we're very limited in terms of clock speed. This one runs pretty fast, so it wouldn't be that hard to just have like code on like a timer interrupt or something like that. This might be useful here. Okay, so let me see. .4 plus 0.85 versus 0.8 plus 0.45. So the pulses are of the same length, it's just a matter of pulse width. So this is actually just PWM, actually. I can just do this with a PWM peripheral. I think this is what we need. I think this will do what we need it to do. So this seems like a voltage and current system. So this is a specific type of protocol here. No, I don't think this is what we want here. It's a bit more of a complicated protocol. There's a specific complicated protocol that this is trying to emulate here that I don't think we can bit bang into this because there's some sort of that's not the correct usage of the word bit bang, that we can't privilege this into doing the WS2812 protocol. What? Like this is also specifically geared towards audio. Makes sense. This is a DSP microprocessor after all. This thing has built-in op amps. Cool. That this thing has a dedicated, basically trig coprocessor. That'll be nice if we choose to do modulation or other DSP sort of effects in the future. It's looking like we don't have, it's looking like we're not having a specific peripheral we can kludge into doing this directly, but what we can do is have one of our timers. So actually, there's a couple of different types of timers here. Let me take a look at this real quick. The programmable advanced control timer is a 16-bit counter with its related auto-reload register. The counter can count up, down, or both up and down. The counter clock can be divided by a prescaler. It to by software, screwed even when the counter is running. Preload register is preloaded. Reading to or writing from the auto-reload register accesses the preload register. Contents of the preload register are transferred into the shadow register permanently or at each update event, depending on the auto-reload preload preload enable bit. You really love electronics documentation. They truly say things like auto-reload preload enable bit. The update bit is sent when the counter reaches the overflow or underflow when discounting, and if the UDIS bit equals 0 in the time X CR1 register. It's good. Take a look at this again. Counting mode, the counter counts from 0 to the auto-reload value. Content of the time XARR register then restarts from 0 and generates a counter overflow event. If the repetition counter is used, the update event is generated after upcounting is repeated for the number of times programmed in the repetition counter register. Otherwise, the update event is generated at each counter overflow. Update event can be disabled by software to avoid updating the pattern registers while writing new values in preload registers. And no update event occurs until the unit bit is with 0. Counter restarts from 0 as well as the counter of the prescaler, but the prescale rate does not change. So, what I'm thinking with this, if we can generate DMA events whenever the counter elapses, we might be able to reload the counter's next value. Sorry. So, basically, how do I put this? There are two ways this can go, and one of them is preferable to the other. Okay, let me use Designer instead. Let me draw it out real quick so you can see what I'm talking about. Let me also see if my drawing tablet is in a convenient place. One moment while I wait for Affinity to load. One moment. Alright. So, basically, the timer counts up. So if we imagine a graph time on the x-axis, timer value on the y-axis, windows, then every unit of time it counts up 1. So for the first unit of time it's 0, then it counts up to 1. Etc., etc. Until it reaches its maximum value. Let's say that is here. So this is sort of its maximum value that it reaches. And after it reaches its maximum value, it goes down to the bottom. does the same thing again. Those are in the wrong. Okay. Okay, so that makes sense. So every time it hits the top here, it goes back down to the bottom. It also generates an update event. That update event, lets us basically run a bit of code that can change something or perform a DMA operation. A DMA operation, direct memory access, is basically a way of saying load the value in this memory address into this other memory address whenever this event happens. And like once you specify that transfer happening, it happens every time, and the processor doesn't need to get involved in it. So an interrupt, which is one of the things we can do on an update event, would allow us to do basically whatever we want, but that means we have to interrupt the processor. We have to stop doing whatever we were doing before to do this new thing that we want to do. And then we go back to whatever we were doing once we're done. A DMA operation is much more limited. We can only basically transfer memory from one place to another, and that has to be sort of specified very clearly in advance. But we don't have to stop doing what we were doing. It just happens in the background. So if we can make a DMA operation happen that changes the pulse width of our system, then that would be ideal. It occurs to me that I should probably explain what pulse width modulation is, shouldn't I? So this is sort of your standard timer configuration, right? You have your pre-configured top value, and you go up there and then down, and up there and then down. Pulse width modulation is you have a pin that toggles on that toggles when the timer hits a certain value. So let's say this is your internal timer value, right? You have your top value, and when it hits the top value, it resets. And then you have your PWM value, and I'll explain what that does in just a moment. You can set it up so this is your internal timer value, and then you have separately you have an output pin. So this is a physical pin on your microcontroller. This is not a physical pin. This is just an internal value that you can't really see on the outside. This is a physical pin on your microcontroller. So it can either be 0 or 1. let's say that this is the line between 0 and 1. Basically, your PWM value here, this purple line tells the pin when to toggle on. So in other words, whenever this timer internal value reaches PWM value, that's when the output pin turns on. So if I put a line here, it's confusing to me what affinity is choosing to snap to. I guess it's snapping to like the center point of this thing. Yeah. Snapping values a little bit, hopefully making it easier to work with. So this is the point where this value hits the PWM line. And so this is the point where our output pin hits 1. And then when it hits top, then the pin goes back to 0. And this repeats. We get the next PWM value. And goes back to 1. Time we reset that, the pin goes back to 0. So this basically creates a series of regular pulses. Where the period of the pulse is equal to like the time it takes to count to top, right? So if you move top up, then that means these pulses are lower frequency. If you move top down, they're higher frequency. PWM controls a different aspect. So if we move PWM up here, right? Now, the point where we hit that value changes. And thus, the width of our output pulse changes. So in other words, this PWM value, the value at which this pin switches on, determines the width of the pulse. That's why it's called pulse width modulation. So basically, the idea is we need a signal with a specific value. So let's say see if I can see a grid here. Yeah, okay. Actually, let me set the grid. This will make it easier, I think. So we want let's say our time ticks are like time ticks are sort of like this. And we want a signal with a specific width. So the properties of these WS2812s, to send to 0, we need it to be 0.4 microseconds on, 0.85 microseconds off. Let's simplify that to just 0.4 and 0.8. So if we want to send to 0, that's 0.4 on, 0.8 off. If each one of these is, let's say, let's say that each one of these is 0.4, right? So we want our signal to look like this. We want our signal to look like this. So 0.4 on, 0.8 off. I want to send 0, 0, 1, 1. So here's 0. 0. And then to send a 1, it's 0.8, and again, we're going to say 0.4. So it's just the other way around, right? Send a 1, we want it to be on for 2 and off for 1. On for 2, then off for 1. And then those read as 0, 0, 1, not quite it. There we go. That reads as 0, 0, 1, 1, right? Because this is a 0, this is a 0, this is a 1, and this is a 1. If we wanted to create this, you'll have to forgive me for zooming in a little bit on this internal value. So let's say we are ticking up each one of these. So if we set the top value, we have to set the top value to, the top value determines, right, what our frequency is. So we want our frequency to be every 3 ticks, right? So it goes 0. So if we just show like what a count would look like, so it's 0, 1, 2, and then we want it to go back to 0. So we want top to be right here. And now, I know I showed here that PWM shows when it turns on. It is easy enough in most microcontrollers to configure it the other way around, so that essentially this would be like it turns off when PWM is hit. So for the first one, we want it to turn off here, which means we want PWM to be here, right? Because then as soon as we hit this first clock tick, we hit the PWM value and it turns off. But that works the same for the first 2 here. But then what happens when we want it to stay on for 1 tick longer? Well, in that case, we need to turn the PWM value up. So basically, our 1s and 0s determine the PWM value on every cycle. Make this a little bit thicker so it's easier to see. So, because the PWM value is higher, that means that the shape here looks different. So for 0 and 1, it's going to be the same shape. Well, the counter value shape is actually going to be the same for the whole thing. I want to move all of these to the front. A bit more of a visible color. We'll make these thicker as well. So this is our value counting up, and every time it hits the PWM value, the signal turns off. Every time it hits top, the signal turns back on. But now when the PWM value goes up, then it hits the PWM value 1 cycle later. So it stays on 1 cycle longer. So as you can see, the pin turns on whenever it hits top, it turns off whenever it hits PWM. The PWM value increases, and so the pulse becomes wider. So what we need to do is every cycle, depending on whether the next bit of data we want to send is a 0 or a 1, change this PWM value. And we need to do that very quickly because we need to do it before we hit it in the timer. So yeah, that's sort of the task that we need to accomplish. We can do this with a timer easily enough. But the challenge then becomes, how do we load it with a new value every cycle? If we can perform DMA into this register, this PWM register right here, then it becomes a very simple problem, right? We just say, we basically just have to convert our values. So PWM would need to be, what is this? 1, 1, 2, 2. So then it's just basically taking each bit of our input and converting it into a byte for the PWM register. So 0 goes to a value of 1, a 1 goes to a value of 2, and so on and so forth. This is a little bit space inefficient because we're using a byte for we're using an extra byte for every bit, but we're not space constrained enough that should matter too much. If we can't use DMA, then we need to have an interrupt to calculate the next bit and put it in the PWM register every time we hit the top register. So I hope that was a clear enough explanation of what I'm looking for here. If not, please do feel free to ask questions and ask for clarification. Let me first check if these are usable for PWM. Yep, we're good. So I'm just scrolling through here looking for more information on the PWM system. Output compare mode is usually what we're looking for, so that means that a pin is controlled by comparing the function value to a certain register. Match is found, the output compare function assigns the corresponding output pin to a programmable value defined by the output compare mode and the output ready. The interrupt status register, generate an interrupt, send a DMA request. So that means a match with that instead of trigger a DMA request. Good. XBCRX registers can be programmed with or without preload registers. Interface mode. Goes to a quadrature input. Again, this is locked into a specific piece of hardware, unfortunately. Seems to be a lot of interesting things you can do with these timers, but I'm not seeing anything that is that might provide a better strategy than what I outlined a few minutes ago. It seems like we can use DMA into the register that I described as PWM in the description is actually... Go back up to it. PCR. I believe that is a capture and compare register. I'm gonna drink a little bit of water, one moment. Lubricants. Okay, so yeah, we can automatically like use DMA to load into the CCR registers. Basically load all the data in that way. Let me just look one moment into these other general purpose timers. I'm surprised with all the specific components they have on here. They didn't have anything to translate bits into PWM values. Of course, I could always be missing it. Phew! Excuse me. Take a look at how quickly we can update these as well, by the way. So these LEDs use 8-bit color. Means 24 bits per LED. Each bit is what, 1.25 microseconds? 1.25 times 24, 30 microseconds per LED. $6,000 microseconds per for all 200, which means 6 milliseconds. Because we can update it at about 160 hertz, so we are totally fine. That also incidentally means that we will need 24 bits times 200. Excuse me. 4.8 kilobytes to store all of the data at once. Of course, we don't necessarily need that. The smallest size that a frame buffer could theoretically be. Is this a... Forgetting the bittedness of our microcontroller. It's a 32-bit, 32-bit microcontroller. Theoretically, we could store this in 150 bytes. Like a whole frame data in 150 bytes. We did it really packed. Or, sorry, not bytes. Words. So a word is 32 bits, a byte is 8 bits, a half word is 16 bits. Theoretically, we could also store it much more easily in 200 words. See, so we have 564K of RAM. The 4.8 kilobits of that would be significant, but not like It's not a deal breaker with the amount of RAM we have. All that to say, we should be able to just use a general purpose timer for this. We only need 16-bit timers. Let's see. And we can use a DMA channel for this. So I would say that we can just use any of these, timers, ideally timer 3 or timer 4. Let me see where that signal gets output. Please, ref, verify that. It'll be OCX ref, it's looking like. Let's see. We are looking for timer 3, timer 4. Alternate function 2. So I guess when they say CH, is that the same as the OCX ref? It does look PA6, PA7. Yeah, those pins free. We have PA7 free. That will be timer 3, channel 2. Take a look. Okay, yeah, that is correct. So we need. I should take some notes on pin meetings. Yeah. Timer 3, channel 2. Call this connector LED_DI. LED the I. I stopped folding them by default. But okay, so that is going to connect there. Import that sheet pin there so that we can just move it directly across here. A6. You have to go up here for that. We're using PA6, PC12, INP3. The other one is connected to C4. ABC12 INP4. Good to document that for later. Oh, water drippy. Okay, so button connections. Can matrix these buttons together? I don't know if we need to, though, strictly speaking. Like, we definitely have 25 pins free. We could just scan them all independently. But also, all it would take is a diode to actually do this right. So, no reason not to. So we're going to do a matrix system. I'm going to do the 45-degree one, and you'll see why in a moment. Okay, so let's see. Buttons are an interesting case. You can do a similar strategy with LEDs, although it's actually easier with LEDs. So actually, let me draw this out on paper before I do it in the actual schematic editor. Draw a little switch. This is our switch. So let me make this a bit smaller. Let's use a simple case. Got this 2x2 grid of buttons. So, some options for how we can connect these. I'll draw the wires in a slightly more contrasty color. We connect these legs to ground. And each of these fits its own microcontroller pin. This is good. It allows you to see the value of any button at any time. But it does require one pin per button. The only way of doing it take the very same LED array change the way it's connected a little bit. Connect it up this way. We then end up with 4 pins going back to the microcontroller still. However, this has some advantages, which we'll get to in a moment. So, basically, this will also let you access all the buttons. Like, you can read the state of any given button at a time. But in order to do this, you need to do some clever stuff, basically. So, basically, the simple implementation. Let's say that you take this line, you make it connect this line to ground, and then you check the status. You have these 2 pins pulled up, and you check them. So if the user has pressed this button, then you'll get a signal coming out of here. You'll get the specifically a ground coming out of here, 0. If you press this button, then you get a 0 coming out of this line. Otherwise, you get 1s on the lines. So you can read just this row of buttons by setting this to ground, setting this line to ground, leaving this line floating, and then reading the status of these 2. You can then switch them so that this one is floating and this one is ground. And now these 2 lines will tell you the status of these 2 buttons. This works great as long as the user only presses one button at a time. We'll get to why in a moment. Now, the question is, why would you want this instead of this? As this sounds like it is a more complicated situation. You have to sort of strobe each one, run one row at a time. And indeed, in the case where you only have 4 buttons, this is probably a better solution. Same number of pins and much simpler. However, this does not scale well. So every time you add a new button, so if I wanted to go from 4 buttons to 9 buttons, let's say, then I would need 9 lines to connect the 9 buttons. Whereas with this strategy, if I go to 9, that's 3 by 3. So we have 3 rows, 3 columns. That's 6 lines for 9. If we expand this to 5 by 5, which is what we're doing, it gets even worse. We need 25 pins for each of these. Whereas with these, it's 5 rows, 5 columns. That's 10 total pins. So in other words, this design scales much better than this design. Now, there are some potential problems that can arise in this design. So I wonder if there's an easy way to... It would be nice if I had like a particular type of circuit simulator. Let me see. Yeah, I don't know if there's an easy way to generate this animation other than just, generating it. But you can look up specifics of the problem if it has you confused. So let's use color coding for this. This line, let's say it's floating. This line is grounded. And the user is pressing this button, and this button. So, this creates a problem. What we should read, what we want to read, is for this to read as this to read 1, I suppose it would be easier to say we want this to be floating. So then we'll read that as a 1 because we have pull-up resistors to pull it up. We want this to be grounded, so it'll read as 0. However, because this line is floating, when we press this button at the same time as this button, so connecting this button makes this whole line here grounded, right? Then pressing this button means that we're connecting something floating to something grounded, which means that this whole section, that's not grounded. And that wouldn't be a problem, except that we're also pressing this button, which means that this section, which is now grounded, is connected to this, which means that this area is also now grounded. And so we read 0, 0 when we should be reading 1, 0. So obviously, this is a bit of a problem. Basically, this means that if the user is pressing more than 1 button at a time, we can run into issues where lines read when they shouldn't. And yeah, with the hardware setup as we have it right now, there's really no avoiding that. However, there is a relatively simple measure we can take to fix that. What if, instead of having these connected directly to a line, I should move these a little bit apart. We connected them through a diode. Did the same thing here. Actually fix the color on that. Same thing for all of our buttons. So instead of just being a button, it's a button and a diode. Apologies, since we are pulling down, the diode should be the other way around. So that's properly balanced. All right, so reset all of these to floating. So now, if we connect the buttons again, the same situation we had last time that caused us issues. So we're acting as if ground is traveling here, but it will be the other way around. So the diode in this case allows ground to propagate this way, but it won't allow ground to propagate this way. Because current current here, right? The current from the pull-up resistor can flow through this way, making this line grounded. However, current from this pull-up resistor can't flow through this way because there's a diode here blocking it. So this stays floating. Since this line's floating, this line stays floating, and then we get the behavior we want. So that is the general idea of how to basically how to make a strobing system for your buttons. I hope that was clear enough on my part. Again, if not, feel free to ask questions. So that is the sort of idea we're going to be going for here. We're basically just going to be implementing the same thing. So actually, I think it would be easier. Okay, let's do this. I have to take a look at what diodes are available. want a surface mount diode because we don't want to worry about soldering it on ourselves. See. Yeah, this should be fine. See if KiCad has this. WX instead of WS. Same price, in stock. Seems fine to me. Really don't need that there. Then we just need to copy that design over, basically. That's so true. There we go. Yeah, that actually won't work. Well, that's a tad irritating. I guess we need to move these switches apart a little bit. No worries. We do is control Y. Let's make sure that that works. Oh wait, that's not. Oh, let me fix that. Yeah, that should be fine. Let's go and mess with the order. Hold on. I want these components to have a sensible numbering order. I want it to be like in sequence and not the component numbers jumping around a bunch. There we go. I think this is somewhat hard to read. How I feel about hard to read diagrams, chat. Maybe it would be easier if I made them different colors. I don't know, perhaps I'm just overthinking it. I think it's fine. Load these directly onto a bus. You'll have to forgive me for being quiet. I'm feeling a bit sleepy. I guess I should be putting 2024 on these now, huh? 2023, 2024? -2024? Yeah, makes sense. That should work. There are tricks we can use to reduce the total number of pins this takes, but given that this is only 10, it's not super worth it. If we were really space constrained, we could do like a multiplexer to reduce the number of, or we could use like an encoder to reduce the number of inputs to 4. And we could use like, I don't know, there's a couple of options, but not really relevant to us. We should be just fine without them. copy pasting these over because it's easier than writing them all out again. Be a couple lower. 5. 5. There we go. A very sleepy electronic stream today. Why these are like bolded by default until might just be a peculiarity. I'm glad to hear it's relaxing. Yeah, this sort of stuff can be quite a relaxing thing to do. That can be relaxing to watch as well. Four lines be enough if we used encoders and multiplexers. Well, the encoder. Okay, so if we're using an encoder, what is it? 5 would mean 3 lines. It would be like 6 total lines, and that's assuming we had the parts for it, which would probably be irritating to find. Could also theoretically use the shift register. We need a weird shift register to use just one shift register for both. We could use 2 shift registers, in which case we'd only need, what, like a... theoretically only like a SPI connection plus like... We could probably do it in like 5 lines if we used shift registers. Again, probably not necessary at all for this. I had a project once where I was doing, it was like a chessboard, and that was like 8 by 8 squares. Each square had an LED per piece plus an extra LED, which was what, like 7 LEDs total, like 7 times 64. That LED matrix I used shift registers for because it was a crap ton of LEDs each. For something like this, we have plenty of pins on our microcontroller. I'm not particularly worried about it. This Probably just stick these in port E and use all these as GPIOs. And these will be the first things that we move if we need to. Yeah, having them all together like this is convenient because it lets us, it makes it easier to do the number crunching to get the values we need. Yeah, basically what's going to happen is, scan 0 through scan 4 are going to be, we're going to, like, output one of those at a time. So one of those is going to be grounded, the others are going to be, we could set them high or we could set them floating, it doesn't really matter. If we set them high without the diodes here, if we set them high without these diodes, then there would be a risk of like shorting if someone put the wrong pin, if someone pressed the wrong button. So much digital logic knowledge flowing back into your head today. Yep. Listen, I was a TA for my undergraduate digital logic class. So if this diode wasn't here, then if we had, say, this line high and if we had this line high and this line grounded and someone pressed this button, then that would be a short, right? But with the diode, current can't flow this way, so that doesn't matter. So floating or high doesn't matter. And then we just check the values of these 5 columns. But yeah, that's just an easy way to get 25 buttons into 10 pins. And if we wanted to add another 2, we could get up to 36. Another 2 would get us up to 45. And at that point, I'd probably want to switch to, like, I don't know, I'd say like up to 16, giving us 64 possible buttons would all just fit on one of these ports. Any more than that, I'd probably switch to using shift registers, which we might get into at some point if we do a project that involves that. Doing this project on stream has definitely been a lot of fun for me, so I do not think I'm going to stop at just one project like this. Place that there. Okay, so the LEDs and the buttons, well, the LED connectors and the buttons are all hooked up. We should probably go ahead and place button matrix. Because this would theoretically be a pure input in this case. With this. These are just debug headers. Basically, I want to be able to stick my logic analyzer on this thing and take a look at what's going on at any particular line. because that will make debugging much more convenient for me. Just to get those in early. I guess we should actually implement these connectors now. I never actually ordered that debugger as well. We want one of these. Planning to build this all on the breadboard first before to test the design? No. Generally, PCBA is cheap enough that I can afford to just get a PCB made as a prototype. My general plan is to just be as careful as possible at this stage, so that the PCB is as likely as possible to work. Hence why I'm being so careful about putting all of the necessary decoupling capacitors and such, and ferrite beads as recommended in the device documentation, starting with all that in. But hopefully this will have a very good chance at working first try. Yeah, some of these components would also be a mess to like break out to breadboard them. Like I need to order a bunch of like breadboard capacitors because I don't have that many in the I don't have that many in CIP, and then I need to put together a breakout board for this microcontroller in particular, which is a standard pinout. I could get a standard breakout board for that pinout, but then it's a matter of like I don't have a heat gun on me right now, so it would be a pain to like heat solder it on. And yeah, and then just like these LED board connectors, I'd have to like crimp specific cables to put those into a breadboard. Like, I could breadboard it first. But ideally it just, ideally it just works the first time. I can get some information on what cable this thing uses. Like, they have it broken out to like breadboard cables.
at the end of that night. I was looking for some trouble, you were looking alright. Every time
So ST Microelectronics specifically wanted me to
I don't think I've ever been so close to a
there.
love like this. I never met someone,
The XNC header.
I never felt this way, ooh. I would take potions, we love. I would cross oceans, all the hurt and the pain. You can take it all away, we love. I would take potions. I would take potions.
That's what we're looking for.
I would take potions. Sipping on a little something, I've been sipping too much. I just poured myself a double and I'm thinking about us. Every time I see your face, I think of what I lost. How could all the little moments that we had be so
Truly incredible modern technology.
met someone like you. I never felt this way.
You don't even have to rotate the header in your mind. You can rotate it right there on the page.
We love. I would take potions. We love. I would cross oceans. All the hurt.
There, yes, this is what we want.
You can take it all away. We love.
It's pretty darn cheap.
I would take potions.
So thank you, Onshore Semiconductor, for your datasheet.
I would take potions.
There we go. This is twice as many, actually. Don't see if we're gonna get too much of use here. Okay, we can just throw together a symbol real quick. It is a J, the connector. Put that in the corner. Also, really quickly, that actually would help. So RTCK is an output, TDO is an output. That is IO. Two more. Generally not connected. You can leave those not connected here as well. That should also be an input, shouldn't it? There we go. In reset should be IO. Why do I have to numbering these? 5, 7, 9, 11, 13. Video is in reset, which is an IO. All the rest of these are ground. Funny. All right. This unconnected and those. Connect supply there. And there.
A million miles away, I hear a sound that's here to stay. My life will never be the same.
The rest of these connect to ground.
On my way. Tonight we'll meet again. Let's stay until the end. Tonight we'll meet again. Don't fear, just take my hand.
They stuff the rest of these into like one big connector.
Tonight we'll meet again. Let's stay until the end. Tonight we'll meet again. Don't fear, just take my hand.
How many pins in total are we talking? 1, 2, 3. Oh no, we don't need these. We do need these. That's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, and we probably want to try and locate the D plus and D minus as close as possible as we can to the pins themselves, because having a bunch of it's bad for noise when you have a long length of copper connected to one of the data pins that's not actually connected to the other side. So I feel like we want to remember to put these two like right next to, so we might want to actually I suppose it depends how we end up laying out our PCB. But I might want to set these to their own individual pin headers. have these connected to a single, I guess, 7-pin header. And then these connected to their own individual, like, 1-pin headers. That would make sense. Move that out of the way. I suppose ideally it would be more of a test point. Should be fine. Gonna have a pin here and a pin here. There we go. So it would actually make sense to have the LED connected to its own header as well. I put in a header for power and ground. Makes sense. It would make more sense to have a 2x5 for the button matrix instead. Here, instead of this, well, that is all of our debugging headers. So if something does go wrong once we've made the PCB, having all of these connections, so this connection has to be broken out. This is the JTAG connector that we'll use to program our microprocessor. The rest of these are all just things that I could connect my logic analyzer to more easily diagnose certain issues that might happen once we get the PCB made and get it back. Yeah, I'm thinking about what's left to do. I think we might be I think we might have about everything done except for actually laying out the PCB. So we have our USB-C connector. We have our voltage regulator, although I might want to switch this thing out. TLB 1117-33. This can only provide 800 milliamps out. I might actually want to replace that with something with a higher current output. Something with like 2 amps out, something around those lines. A 3.3 volts out and 2 amps. Let's see what we got in that range. Looks like we've got a few options. Let's... see what the deal is with this. High voltage when output voltage is greater than or equal to 3.0 volts. That's 4.3 volts minimum, which will be fine for powering it off of USB. Pull 2 amps from it. Other recommendations for C in and C out. I should probably also put in some Zener diodes for overcurrent protection and things like that. I'll have to look into that. You know what? I've been streaming for about 4.5 hours. So I think it is about time to call it for the evening. So, go back here. I hope everyone had a good time at stream today. Let's see, I know I had a good time doing it. If you enjoyed the stream and haven't already, don't forget to drop a follow so you can get notified next time I go live. We have a Discord, !Discord in chat, and you can find that. You can also follow me on Mastodon. That's at Digiment at mastodon.social. I'll be back on tomorrow. Sonic Rush Adventure. We started that, don't remember exactly when. I don't think it was exactly last Sunday, but it was sometime during my sort of soft break. And yeah, it's a lovely game. Can't wait to get back to it. I don't think it'll last too long. And after that, the game we play next will be determined by y'all. There is a vote open in the Discord, a forum channel, where you can propose new Sonic games that we could play afterward, or vote on them. And you realize that you also probably have the knowledge you need for design projects. Yeah, absolutely. You know, I would absolutely recommend, if you have any interest in electronic stuff, be safe about it, but absolutely do experiments. You know, if you have the means to do so, making mistakes and figuring out why you made those mistakes is one of the best ways to learn. But yeah, I think that's all I have for y'all this evening. Once again, I hope you had a good time watching the stream. I will see you again tomorrow. And hope you have a wonderful evening. Messing with the 120 volts. Yeah, don't mess with that. Listen, you've seen the kind of voltages I like messing with. Yeah, you don't want to get anywhere near that kind of voltage. I would highly recommend keeping yourself as far away from wall power as possible. But yeah, once again, hope everyone has a good evening. See ya!